All right, so today we're talking about trees, specifically mathematical trees. And this one right here, this is a tree. This over here is not a mathematical tree. Obviously, it's a real tree, but the reason is that there is this cycle that exists in here, and trees don't have cycles in math. So we have two definitions here. Both of them work. One of them is a minimally connected definition. It says a graph is a tree if and only if, which is abbreviated IFF. It is connected, but deleting any of its edges results in a disconnected graph. So for example, if we have this right here, that is definitely a tree, but if I got rid of any of these edges, like if I disconnected this edge, this node would be all by itself, or if I disconnected this node, it would be all by itself. So deleting any edges gives you a disconnected graph. That is a minimally connected definition. The other definition is that a graph G is a tree if and only if it contains no cycles, but adding any new edge creates a cycle. So there is no cycle here, but if I were to add any edge like here, then all of a sudden you have a cycle that you can just spin around here, and you don't want that in a tree. And then fun fact, every tree on n nodes has n minus 1 edges. So for example, there are n equals 4 nodes here, and then there are edges is equal to 3. 1, 2, 3. It is just always going to be one edge fewer than a node. Okay, so something that we might run into is asking the question of, are these the same trees? And in this case, this green tree and this pink tree are the same. And the reason is that if it is unlabeled, meaning I don't care which node is which, like this one is not more special than this one, they're what we call isomorphic, meaning that I could move these edges around. Like you could imagine me kind of stretching this edge up and this edge up, and then we end up getting kind of a green tree that looks very similar to the pink tree. Then we consider them to be the same. So this green one and this pink one are definitely the same. That is not the case if all of a sudden they are labeled. So this is node A, and A has a degree of 3, where this node A has a degree of 1. These would be considered different graphs. So if trees are labeled, then they must be isomorphic, even considering those labels, in order to be considered the same. This leads us to something important called Cayley's theorem. And Cayley's theorem says that the number of labeled trees on n nodes is n to the n minus 2. So if I have a labeled graph, so like these, not like these are unlabeled, a 4-node tree, there are 16 different labeled graphs, and there are 125 that have 5 nodes. So this is a good exercise for you. Find the number of unlabeled trees on n equals 1, 2, 3, 4, and 5 nodes. Pause this video because I'm about to show you the answer if you want to try that. For n equals 1, it's literally just a dot, so there's one of them. N equals 2, there's only one. N equals 3, there's also only one. Occasionally I will get people being like, no, but what about this one? But these two graphs are isomorphic, because you can imagine this edge just kind of like flipping up here, and then you'd end up with the same graph. On n equals 4 nodes, there are 2 different ones, and a nice way to see this is to count the degree. That's what these little numbers are, where you have 1, 2, 2, 1, and here we have 3 1s and a 3. So those are definitely different. On n equals 5, there are 3 different ones. And n equals 6, I haven't even drawn all of them here, but I think that this is a useful one because up here I said that these are different because I have 1, 2, 2, 1 and 3, 1, 1, 1. Notice these two are very different graphs because you'll notice I have, if you look at this 3 degree, gracious, I'm bad at counting. Did that in class too, man, embarrassing. Anyways, this 3 degree node has a string coming off of it of 3 nodes, whereas this 3 degree node only has 2 on either end. And notice here there's 2 3s and there are 4 5 1s in each of these graphs. So that is not necessarily sufficient. And also I don't believe I've drawn all of the 6 node trees here. Just wanted to illustrate that. So if they're different, for sure, they're different. If they're the same, they might be different. Okay, then what we have are what we call spanning trees, and then what we're going to care about are minimum spanning trees. So a spanning tree is, if I have this graph here, a spanning tree is any set of edges and all of the nodes such that you're able to access all of the nodes. So all three of these are spanning trees of this graph. I can get from A to every other node here. I can get from B to every other node, same thing down here, same thing down here. And what we care about with spanning trees is often what we call the minimum spanning tree. So imagine that these are houses and I need to connect them with electricity somehow. And I know that I can get between A and E here. I can also get between A and D. I can get between A and B. But think of these weights on these edges as the cost it's going to run me, right? So A and E are cheap to connect. I only need to pay $1 to connect them. E and D are expensive. Maybe there's like a mountain in between them. I don't know. I can get there, but it's going to cost me $8 to do it, or 8,000 or 8 million. I don't know. Think about it as you will. So the minimum spanning tree is the cheapest one. None of these are a minimum spanning tree. This one is 4, 12, 16, 19. That's kind of expensive. Here we have 8, 12, and another 6 gets us 18. This one would be 5 and 6. This one is 11. The actual minimum spanning tree you find by picking the cheapest edge, building that, then building the next cheapest edge, and the next one, and the next one. Now notice I had 2 3s. It doesn't matter which one you pick, because if I'd done this one first, then I would have ended up doing this one. The trick is you cannot form a cycle at any point. So let's look at one more graph. So here's another graph that we will experiment with, but also this is the official algorithm. It's often called the greedy algorithm, and it is just for finding the minimum spanning tree. So you start with the edge of least weight anywhere in the graph. If there are 2 or more, pick any of those. So in this graph, we have 1, 2, 3 that are all each weight 3. So I'm going to randomly pick this one. Add the edge of least weight that has not already been chosen and does not form a cycle with any of the previous edges. So I'm going to make the 3s definitely part of my spanning graph. And now I need to select 4s. I have AH, BC, CD, and EF, except I can't pick this one because if I did, I would form a cycle here and y'all don't want that. So we're definitely not going to select this one. But I will end up selecting CD and then AH and then BC. And I am now left with just getting to G. Now I have several ways of doing that. Neither of the 5s are going to get me there, so I don't care about them. I've already connected everything that is connected to those 5s. They are unimportant. But I could use HG or I could use DG. It doesn't matter which one you pick. As long as you end up with a spanning tree that is of minimum cost, you are fine. But notice that this white spanning tree right here is equivalent, I guess, to, it's not the same, but it is equivalent to if instead of choosing DG, I had picked HG. So sometimes there are more than one minimum spanning tree, but it will always obviously have the same cost once you get there. You have a homework assignment in Google Classroom. Let me know what questions you have.